Hey,
Oh,
Mark.
we're live. Sorry.
We are
I
live.
was prepping my desk.
Yeah,
All
we're
right.
live.
Hi, Verge. Hi, everybody.
Hi,
All right.
everybody. Welcome back.
All right. So, on to our slideshow. I am Mark Raleigh from Ryan High School in Denton, Texas.
Verge Cornelius, Lafayette High School, Oxford, Mississippi.
We are wrapping up. We're on the downhill slope of week, I guess, 2.5, week 3 here. Finishing up Unit 8 today and tomorrow. And then next week, we will start our review. Those schedules are online now. I may put a link in the Dropbox to that as well, because we do have a full schedule finally published. So,
Excellent.
all right, our now old slide of exam information that was new last Friday. 45-ish minutes, May 12th, and obviously during those review sessions, we will let you know things as we find them out, right, Virgin?
That's right. We might find some stuff out tonight in terms of viewership. We have an optional meeting and we are going to figure out like which AP Lives are getting watched the most. So thanks for you, everybody out there watching.
And here's an optimistic slide. Unfortunately,
Oh.
we got a couple emails yesterday that in the circuit that was in the Dropbox, V of t was in terms of x. V of t is now in terms of t. I updated it this morning. So if you must have a pristine copy or you want a copy to have for future practice or review, you can go back in and drop that, go ahead and download it again. And if it didn't take, please let me know. But I believe I corrected it in both the file and in the key. So I guess we will look at a new video here tomorrow and hopefully get up to 1.
And that's actually a shout out to several teachers who pointed it out to us. Some of them were actually our friends and we ignored them until somebody we didn't know contacted Mark and we were like, okay, we'll fix it.
Yeah, and partially that was my fault because when I tried to update it yesterday, it didn't take. And so I thought we'd caught it soon enough that maybe we could have slipped it through, but oh well, here we are.
Oh well.
So we are back to introductions and correction instead of introductions and banter. Our warm-up is going to blend into our lesson today, so don't blink, don't fast forward too far. And we were talking about 8-4, finding the area between curves. 8-4 specifically in the CED is in terms of X, but I believe our assignment in the Dropbox may include some in terms of Y.
That's correct. Mm-hmm.
And then we're going to tie this back. Of course, it's finding the area between curves. Shockingly ties back to 6-5, where we interpreted area under curves. And then we'll wrap up and let you know what's in the Dropbox exactly. So here's today's warm-up. Again, adapted from yesterday's materials.
So normally I tell a joke at this time, but this week I've really been talking about the Mobius strip, and I got some other emails from students yesterday, and I'm going to go into the Mobius strip a little bit later in the lesson, but Mark said he had a joke, so go ahead, Mark.
I think I'm going to save the joke for the next slide because I think this one most people will be done already. But and I also want to explain the weird spacing. I do this in my class a lot. I'm sure Verge does too. Sometimes the wall of text a problem presents is a little overwhelming, and so we've kind of parsed out what you do with underlining or boxing of the pieces. So we have water's pumped into an underground tank at a constant rate of 8 gallons per minute for time 0 to 3 minutes. And find and interpret in the context of this question. So that is our 8 gallons per minute times 3 minutes.
So can I try to answer that?
Sure.
Okay, so 8 times 3 would get me 24, and that would actually be 24 gallons. And that would be that 24 gallons have been pumped into the underground tank over those 3 minutes.
Excellent. So now we take away what we gave you and put a little more in. So now water's leaking out of the tank at a rate of square root of t plus 1 gallons per minute for 0 to 3 minutes. Find and interpret the following in the context of the problem. Integral from 0 to 3 square root of t plus 1 dt. You already did this if you did yesterday's extra work, so you can go find that, or you can work it right now while I tell a poor joke, but it's a joke. So Verge, do you know what 0 said? Do you know what 0 said to 8?
I actually do. This is completely unrehearsed, everybody, but I'm going to tell you 0 said to 8, hey, I like your belt.
Nice. Now the follow-up. What did 11 say to pi?
I know this one too. This is my favorite. Nice hat.
See, I like nice beret if you draw it with the curly.
Or a tam. How about a tam?
All right.
Oh, I could see a student out there making a little cartoon about this and then taking a picture and emailing it to us. That'd be so cute. Okay.
And before you go online talking about our quality of our jokes, you get what you pay for. All right.
Cosine of 90.
Degrees.
Yeah. Degrees.
All right. So water is pumped into an underground tank at a constant rate of 8 gallons per minute. Water leaks out of the tank at a rate of the square root of t plus 1 gallons per minute for 0 to 3 minutes. At time t equals 0, the tank contains 30 gallons of water. How many gallons of water are in the tank? So we've really amped it up now. This is the full problem. If you did do the previous slide, right, you have this. Let me get in here. That integral from 0 to 3 of the square root of t plus 1, that was actually where we ended yesterday, and I believe it was 18. Is that correct, Verge? It was 18 gallons leaked out in that 3 minutes.
I honestly, now I got to look it up. Sorry.
That's okay.
Dun, dun,
So.
dun.
Should have saved the joke for this. All right.
Hold on a second.
I'm racing you now. I don't know. Anyway, so while she's doing that, so now what's changed is we're asking for how many gallons of water are in the tank at time 3. So now we have to put it all together because we know we're starting with 30.
I had a suspicion it was a fraction. It's actually
14 thirds.
Correct. Yep.
Yeah.
So that definite integral was 14 thirds.
Yeah. Oh, of course, because it's 3 halves times 2 thirds. Good job. All right. So we start with 30 gallons. We found on that first slide that we're pumping in 24 and we're taking out 14 thirds. And so here's a graphic interpretation as well. So you can see there's our 30 that we started with, and I've highlighted it up here. There's our 8 times 3, which is the 24 coming in, minus, and I've underlined this in purple, how much is leaked out. So Verge, where does that represent on this graph if you look at this graphically?
Well, the 8 times 3 is that whole big rectangle with a base of 3 along the x-axis and then going all the way up to 8. So that's got an area of 24. And then the definite integral is that purple part. That's the 14 thirds. And that's how much has leaked out over that time period. So when the question asks, like, how many gallons of water in that tank at that moment in time, we can just go ahead and go ahead, Mark.
Oh, I was just, So the net change is just this area in between.
The green part,
the green, which is why I did this whole part of this expression in green. And then we do have to add the 30 in. So.
But we thought this was a really nice tie-in to what our lesson is today, because our lesson today is area between two curves and curves that are in terms of x. And that's exactly what that green part is there. And that Mark created. I'm grabbing at my screen right now like I would at my board in my classroom, but that right there is the area between curves. And so you know, we did it kind of by piece, but now let's think about some stuff from geometry or middle school to help us really understand how we might figure that out before we go back into calculus.
And also, right before we do that, again, yes, we said between curves, and we know that's a straight line, but a line is a solution curve for the equation y equals 8. So. So here's our continued warm-up extension, right? And we're asking you to find the area of each shaded figure, or the shaded area of each figure, or shaded is colored in because the entire right picture is colored in. And Verge, you had something to take care of some time while students read this and thought about this or paused us.
Oh, well, not necessarily.
Oh, were you saving it for later?
Okay. I'm going to save it for when I turn on my document camera. I think we can kind of talk through this. They can pause it themselves and think about it.
Good.
But then we can just start talking, I think.
Okay. So the radii of this washer are 5 and 2. I'm assuming 2 is the inside, as 5 is the outside. Does not give me units. That does not bother me much. And so what is how would we find the area of just this region?
Well, when I look at that, I think to myself, I need to find the whole big circle and I need to subtract out the little circle. So pi r squared is the formula for area of the big circle. So that would be pi times 5 squared, which is pi times 25, which is 25 pi. And then find out the area of the little circle, which would be pi times 2 squared or 4 pi, and then subtract. You got to subtract that out.
All right. And I don't think I'm gonna grab the camera for that. I think
21 pi.
25 pi minus 4 pi. Sure
Yeah.
sounds like 21 pi to me.
Okay. And then
this one, I think I may put the camera over it.
Yeah.
So go ahead and start talking about that one if you'd like.
So that one with the orange actually is the key in basketball. When you're under the net, and depending on whether you're offense or defense at the time, you have to be or allowed in it or not allowed in it for a certain amount of time. So some people who play sports know what I'm talking about, but we would want to find that area. And we're told that the area of the rectangle is 180 and the longer side is 15. So, and Mark actually looked it up, and this is definitely the correct dimensions for.
Although probably not to scale, right?
Not totally to scale, right? But pretty close. So if the area of that rectangle is 180 and the longer side is 15, then the shorter side would be 180 divided by 15 or 12. So we know that area is already 180. We need to add to it. Oh, we're not subtracting this time. We're going to add to it that semicircle on top. So you have to really know what you're looking at before you can make any decisions about whether you're adding or subtracting. So, I like how you have sound effects, Mark, when you're trying
to do always
the same thing.
yeah, it's funny. You can hear them when I do videos for my Algebra 2 guys, so I cancel.
So the radius is half of 12. We're going to need that radius for our semicircle area. So we have the radius is equal to 6.
All right. So our area of our rectangle is 180 square feet, and the area of our semicircle be 1/2 of 6 squared pi, or 18 pi square feet.
Yep.
All right. And they wanted the area of the shaded region, so total area is 180 plus 18 pi feet.
Feet squared.
Oh, yes, thank you.
You know, while that's up there, I don't know if you can grab it and kind of slide it across and maybe just kind of jot down the answer for the washer. Yeah. So the answer for the washer. Oh, look at there. You already have it written down. Yeah. So those folks who are watching our video right now, our teacher colleagues and things like that, or maybe even some BC students, they know exactly why we might pick something like a washer and think about it, because that's how we build volumes. It's a topic that's actually been taken out of the AB test for this year, but it's a very important topic for calculus, and it's definitely going to be tested for BC students this year. You know, I love washers. I pick them up all the time out of the street. Isn't this a huge washer, Mark?
I can't see your screen.
Oh, I was holding it up to my
I know,
face.
I had you minimized. Oh, there you are. Hi.
Okay, I'll show it. Can I grab the?
Absolutely. Go ahead.
Okay.
Grab the screen.
Did you want to actually, Mark, while you had your screen up, did you want to show a little bit about like the formula for how we calculate area, like just abstractly with calculus, or?
Sure.
Yeah, like some generic f of x, some generic g of x. Yeah.
So, all right. Let's go. And I'm not going to do a linear curve just because that phrase bothers people. Oops, that X skipped leg day down there. Okay. All right. And let's just do something fun, like a couple interlaced parabolas or something. Please don't try to figure out what the equations of these curves are. They're freehand. I have no clue. All right. So we'll let that be g of x. And then let's come in.
Because now what Mark's doing, is he's really creating a problem for which we don't know the formulas from geometry. We don't know, oh, that's a circle.
Although some people
that's
might, because I said they were parabolas. So they're not parabolas. They're unknown curves.
Yeah. They're unknown curves and we don't know the formulas. They're not easily accessible from our mind in terms of the geometric formula area of a rectangle or a circle or a semicircle or a triangle. But we could still figure out the area of that enclosed region that he's shading in right now using calculus. And
so if we wanted to find that, so what I would do is, and I did these intentionally at 1 to 3, and I can change these. We can go A and B and make them just completely abstract.
Mm-hmm.
There's the sounds again. I'm not going to be able to not do that. All right, so I'm thinking that if I could start with that red area, if I could do that, how do I find that area? If that's y equals f of x.
You would integrate. You would integrate, set up a definite integral from a to b of f of x dx.
Right. And then what I want to take out is that piece.
Mm-hmm.
So fortunately, I have lots of paper still. maybe using the eraser a lot more in and what I really want to take out is these pieces, right?
Mm-hmm.
But those pieces are just the areas between g of x and the x-axis. So integral from a to b of g of x dx. So to get this, I want to subtract those from the red. So to get my green area, I simply want to do the integral from a to b of f of x minus g of x with respect to x, and that is top minus bottom, right?
Mm-hmm.
Very similar to the washers, right? If we shrink this down, it's outer minus inner, and top minus bottom. Also, I don't know how good these pens are going to work at this, but if I hold it up like that, that's what it looks like if you're doing it in terms of y, and it's right minus left. So
yeah. Okay, so that's excellent. That's exactly what I wanted you to show, how we can go kind of from our geometric knowledge to our calculus knowledge. And I'm going to go ahead and grab the screen now.
Excellent.
And this will stop the other screen sharing. So
yes,
that's okay. And here's my little sticky note. It's our 12th AP Live, Friday Eve. It's kind of funny, like we don't even know what Friday is anymore. But before I go into working some of the problems off of the circuit, I did want to do a little bit about this Mobius strip idea. And this right here is not a Mobius strip. This right here is not a Mobius strip. To make a Mobius strip, and I've had several students send me their stuff, we would not want to make a loop like this. We would want to make a twist in the loop, okay? That will make you your Mobius strip, and then you need some tape, okay? Very high tech here, like all my stuff. You need some tape to tape it together. And when I said the joke about the chicken, why did the chicken cross the Mobius strip or something? It was to do what? Do you remember the punchline?
To get to the same side.
To get to the same side. If you take a marker, and I'm not going to do this all now, but if you take a marker yourself, those of you who've emailed me about your Mobius strips, and you kind of take that marker and you go all the way around the Mobius strip.
You can actually keep your marker pinned to the table and just drag the strip through.
Oh, that's cool.
And then there's no accusations of, oh, when you picked it up, you did something illegal.
Yeah, so try that yourself, because tomorrow we're going to finish up what I know anyway about Mobius strips, which will involve cutting on this line that you're going to make. It's a little bit different than if you did it on this kind of a loop. You see what I mean? It's going to be a little bit different. All right, that's good stuff to think about. This circuit that we're going to go ahead and work some problems from is in our shared folder. It's the area between curves. And I'm going to go ahead and kind of jump into the middle of the circuit and start with what I have as number 4. And I've picked these intentionally just to give a nice variety. Oh, Mark, here's that washer. That's a pretty good size washer, huh?
That is.
Yeah, I know. I love those.
How much thickness does it have? Because the shadows just...
It's pretty thick.
Oh yeah.
I don't know. Maybe 3 centimeters or so. Yeah. It definitely fell off of some piece of farm equipment or something.
And that always brings up that philosophical conversation I have when we're doing cross sections that are discs of when does a disc become a cylinder, at what thickness?
Oh,
because they are the same, right? I think generally tuna can is the consensus that
would be a cylinder. Okay. All right, so these are some problems to practice, and there's plenty more on the actual circuit, but this is the idea of finding the area between 2 curves. So it says here, find the area of the region completely enclosed by the graphs of y equals x and y equals x squared. So the directions here are to sketch and shade without the use of technology your shaded region. And so y equals x is just a diagonal line. Y equals x squared is a parabola. And if you went ahead and put that on your graphing calculator and looked at it, this would be all kind of smushed in the center. You would need to kind of change your window pretty well to get a good view. But in any case, I know that the parabola is underneath the line on that interval from 0 to 1. And how do I know that? I always think about what's going on at a half. So on y equals x, that's the point a half. But at y equals x squared, that's a point a half what?
1/4.
Yes, so 1/4 is less than a half. Anyway, it's just good little things to know to help you make your graphs. In any case, if I wanted to find that area, I would set up the integral from 0 to 1, because that's where my intersections are, of my top function, which on this interval is x, minus my bottom function, which is x squared on the interval. Sidebar, if you mess it up and do bottom minus top, what do you think the sign of your result is going to be?
Well, that'd be kind of like taking 4 pi minus, if we'd done, instead of doing 25 pi minus 4 pi, if we'd done 4 pi minus 25 pi, I would have gotten negative 21 pi.
Right. So sometimes students just don't even like pay mind to which one's on top and which one's on bottom. They just make their answer positive at the end. So anyway, it's just, something to think about as you're working through. So here, anti-differentiate. So we end up with a half x squared minus a third x cubed. And we're going to go ahead and evaluate that from x equals 0 to x equals 1. Substitute in 1, doing a little f of b minus f of a, and then substitute in 0. This is polynomial, and so that's going to just end up being minus 0. So I have a half minus a third, which I believe ends up being a sixth. Go ahead, Mark.
Oh no, it was just the fractions.
Oh, the fractions.
Oh no. 3
oh
6
no, my
2
pen
6.
is my pen. I didn't check my ink level on my pen before I started. I can tell it's running out. So
should I hand you one?
All right. This is not the next consecutive problem. This is just another problem that I thought would be a good one to work out for everyone. This one is number 6. It says find the area of the region bounded by the parabolas y equals 2x minus squared and equals x squared. This one really reminded me of the one that Mark did. This one really reminded me of the one that Mark did a few days ago, or I honestly can't remember, but it had a 3 in it, and we sketched it very quickly. It's an upside down parabola. This one is going to have intercepts of 0 and 2. This one right here, y is equal to x squared, is opening up. And then this is the enclosed region. Definitely both intersecting at 0. Where else might they both be intersecting? Well, you can set them equal to each other to see where they're intersecting. Solving the system. Add your x squared to both sides. Get basically x equals x squared when you divide both sides by 2. And then you can even do this by inspection. What squared is the same as itself? That's what it's saying. 0 times 0 is 0, and 1 times 1 is 1. So I'm thinking that this would be at 1. You can also bring everything inside and factor, but that would be probably the way I would do it, just by inspection.
Yeah. Also.
All right. So then go ahead, Mark.
I was just going to say, also, since the one that's opening down still doesn't have a stretch factor on the x squared, you know that their first step is 1, 1 on each of them, is 1 over and 1 up too. So
that's nice.
There's some geometry you can use there.
Yeah.
Because it's a reflection.
Exactly. So we would have 2x minus x squared, this kind of my top function on that interval, and then minus my bottom function, which is x squared. That's going to be my entire integrand dx. I might go ahead and combine like terms before I'd anti-differentiate, and I'm going to just leave it at that because that's very similar in terms of the finishing out the problem compared to the last one. You can definitely finish that out for yourself as an exercise. Any other comments on that one, Mark?
No, other than no, because I'm sure you're going to have an example that I see something that might happen. I'm sure you're going to touch on it.
Well, I've said it before and I'll say it again. I'm never going to let one of these live sessions go by without doing trig. So here we go. Find the area of the first quadrant region enclosed on the left by the y-axis, above by the graph of y equal cosine x, and below by the graph of y equals sine x. I don't know if this is the one you're thinking of, but definitely
if it doesn't come up, I'll mention it.
Okay, this is definitely a little different than the one before anyway. So above by the graph of y equals cosine x. So that means here's my graph of y equals cosine x, one period of it anyway. Below by the graph of y equals sine x, I'm going to go ahead and do one period of sine x, roughly. So there's my x-axis and there's my y-axis. These are challenging for students to figure out exactly which region we're talking about, because now a lot of stuff is getting enclosed, perhaps. So area of the first quadrant region enclosed on the left by the y-axis. So here's on the left by the y-axis, above by cosine x, and then below by sine x. So that's my region right there. And that's what I would want to try and figure out the area of. I need to know my interval on which I need to integrate. So I need to know where these two are intersecting. Where's this?
And I'll change that to you should know.
Yeah. Oh, definitely. Yeah. You should know where sine is equal to cosine. Where's sine is equal to cosine at pi over 4, 45 degrees. Okay. So that's happening at
I am going to interject here.
Yeah, go ahead.
I love just letting people know, because it's out there. Your teachers probably even said it, but you missed it, that the cofunction is the complementary function. So these are going to be equal. Sine and cosine are always going to be equal when the angles are complementary. And if they have to be complementary to themselves, because they're both x, it has to happen at that pi over 4 or 45 degrees. Just, I like
That's what the co stands for. Yeah.
Co stands for complementary there.
And cotangent and all the cos. Yeah.
It's kind of like having a co-host. You complement each other.
Oh, that's so true, Mark. Can we be done for the day?
Just shut her down. And out.
And done. Okay, now we got to finish this problem. Okay, so this intersection here is at pi over 4. So my definite integral would be the integral from 0 to pi over 4 of my top function, which is cosine. So cosine of x minus my bottom function, which is sine of x dx. Now this one I actually am going to finish out because you do need to remember what these different values are for the cosine and the sine function. When I anti-differentiate here, the integral of cosine x would be sine x. And then minus the integral of sine x would actually be negative cosine x. And then we want to evaluate that from x equals 0 to x equals pi over 4. And I'm going to actually move this down just so that we have plenty of room. So we really have sine x plus cosine x. And we're trying to evaluate that from x equals 0 to x equals pi over 4. So sine of pi over 4 plus cosine of pi over 4 minus, and I don't want to just be like, oh, it's 0, so I'm just not worried about it. I'm very worried when I have to plug in 0 to anything but a polynomial. So sometimes I get 0 and sometimes I don't. So sine of 0 plus cosine of 0. Sine of pi over 4 is root 2 over 2 plus cosine of pi over 4 is also root 2 over 2 minus sine of 0 is 0 and cosine of 0 is 1. So this final result, root 2 over 2 plus root 2 over 2 is root 2, and then minus 1. That's my final answer for that one. Mark, would you want to say anything else?
No, other than if you don't like that as an exact answer, I'm sorry. That's it. You can get an approximation from a calculator, but that there be exact.
And math teachers, we love those numbers. Don't bother us at all. Like we love those kind of answers, right?
Yes. you can find square root of 2 on a ruler. That's not a problem.
All right, got 2 more. So here's the next one. This one is find the area of the region enclosed above by the bell-shaped curve of y equals 8 divided by 1 plus x squared, and below by the horizontal line y equals 4. Okay. So if I'm talking about the curve here, this bell-shaped curve, thinking about what Mark does, plugging in 0 for x, you would have an output of what?
8.
Yep. What about plugging in 1 for x? What would you have an output of?
That'd be 8 over 2 or 4.
Mm-hmm.
Ooh, that actually hits our line.
Yeah, so that's not 4, is it? That's like 6. I don't know what's going on with that.
Logarithmic graph paper.
Okay. Probably so. So yeah, so that's good. So in fact, this function is even, which means that f of negative x equals f of x. So if I plug in -1, what do I get for my y value?
Positive 4.
Still 4.
That negative
right?
1 squared is still 1.
Mm-hmm. So I have this bell-shaped graph.
And we've seen this graph before. This was on our slope field match. That was one of the multiple choice.
It sure was.
It wasn't 8 over 1 plus x squared. It was 2, I think it was 2 over 1 plus x squared, or 1 over 1 plus x squared.
Right. And watching us right now ends up becoming a mathematician dealing a lot with probability and stuff like that. This is a curve that you see a lot. So in any case, you might remember this kind of a curve from Algebra 2 class when you're doing standard deviations and things like that, or even in an AP Stats class, something like that. Okay, so the area that's enclosed by these 2 graphs or these 2 curves would be that area there. And my symmetry is having issues right now, but that's a little better. There's symmetry on both sides. I said this was even. So one thing that I might do if I have to figure out that area is I would just go figure out the area of one of the sides and then double it. So in any case, I really could figure out the integral from 0 to 1 of my bell curve, 8 over 1 plus x squared, that's on the top, minus 4, that's on the bottom, get that result and double it. That's probably what I would do. I usually exploit symmetry anytime I get a chance. Mark, do you have anything you want to add about that, or?
No, actually, I was just thinking if I wanted to actually put the equation for the bell curve, because that's not the bell. It looks like a bell curve. It's a
Sure.
similar shape, but it's not the. Because I know the students are fine with it. We're going to get emails from teachers.
Well, it says the bell-shaped curve. It doesn't say the bell curve.
I know. But
so all you people who are composing emails right now can just hit delete.
just back, tick, 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 tick.
Virgin Mark, you're doing a great job. You can send us that. Okay. So I like this example though. And again, I'm going to double it at the end. I hope I remember to do it. I could write a 2 out front, but it's going to get a little bit crowded. I in particular really want to talk about this, this part right here, the integral from 0 to 1 of 8 over 1 plus x squared dx.
Yeah, here's your embedded review, right?
Exactly. And I'm actually not going to finish out this problem right now, but I do want to talk about this, how to work this part. Again, this right here with this 2, I would ... I would finish that one off some other time. But this right now, I want to really talk about what this is. So the integral from 0 to 1 of 8 over 1 plus x squared, well, I can go ahead and slide that 8 out of the integral symbol. And hopefully this integrand reveals itself to me. Oh, antiderivative of 1 over 1 plus x squared. That has nothing to do with U substitution.
No, in fact, U substitution is gonna, without using the U substitution you would use means you know what this is.
So, and it's not going to be a log or anything like that. You know, this is actually.
I'm feeling a gentleman from the South.
You are?
Somebody who spent some time in the sun.
Oh, a tangent?
Yeah, a tangent. Yes.
A tangent.
Yes.
I was thinking of an inverse tangent, actually.
Oh, yes.
So, you know, not just tangent. That's why I was confused.
Arctangent, yes.
This is, arctan. Yes, that's right. So the antiderivative of this 1 over 1 plus x squared would be inverse tangent of x. This 8 is that coefficient. And then to evaluate it from x equals 0 to x equals 1, it would be 8 inverse tangent of 1 minus 8 inverse tangent of 0. So what does inverse tangent of 1 mean? It means where is the tangent equal to 1? Where, radian-wise, is that happening? And actually, the tangent's going to equal 1 when the sine divided by the cosine equals 1. So when the sine and the cosine are the same, which we already just did, we know where it is.
Very
Go ahead, Mark.
coincidental. The slope is 1 at pi with a ray. It has a pi over 4 angle, right?
Mm-hmm. So. And you told that joke about pi and 11, and now I'm just making all these little 11s with chapeaus, berets. Okay, inverse tangent of 0 is 0. That's where the tangent equals 0. So my final answer here for this portion, and this portion only, would be 2 pi. 8 times pi over 4 is 2 pi. Again, I would still have to integrate from 0 to 1 of this 4, subtract, and multiply the whole shebang by 2. And we can do that some other time.
I think 4 pi minus 8 is where it's headed. Just.
Yeah, that's the final answer.
Yeah. Or actually, yeah, 16. Is it 8 or 16? No, that was with the 2. Yeah, that's right. That's 4 pi minus 8.
No, you're right, Mark. It's actually not hard to do that stuff in your head, which Mark just proved. So,
thanks. As evidenced.
As evidence, Mark just did it in his head. Yeah.
There's been plenty of good places to end this video today. All right, you got one more there.
This really is the last example. Okay, so this one says, find the area of the region enclosed by the graphs of y equals square root of x, y equals 2 minus x, and y equals 0. And, you know, I'm sketching them all by hand. I've been doing calculus for 30 years. I've been studying math a lot longer than that. If you need to slap these into your calculator and take a look at what's going on, that's totally fine, especially 2020, where we're allowed to use our technology. It takes time, though, right, to get out your calculator and turn it on.
The more you can do without it, the advantage is yours, right?
Huge advantage, right? So equals square root of x is my square root curve, something like that. And then y equals 2 minus x is a linear curve where it's kind of coming down. It's got a negative slope of 1 and then this y-intercept of 2. So it's kind of coming down like this. Okay. I'm drawing it intentionally vague. So anyway, Mark doesn't like it when I put the arrows on my curves, but he'll get over it. Okay. All right. So find the area of the region enclosed by the graphs of y equals square root of x, y equals 2 minus x, and y equals 0. Y equals 0 is the x-axis. So what's interesting about this problem is that I'm not going to find this area right here. That would be enclosed by blah, 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 and x equals 0, the y-axis. I'm in fact going to find this area right here.
But those curves aren't over each other, Verge.
I know. That's why you have to like be able to look at stuff and see what's going on. So this one is not really like the washer problem. It's more like the basketball key. Yeah. Yeah. Okay. So anyway, there's a way to do this in terms of y, but if you want to stay in terms of x, what you would do is you would say, well, I'll just figure out this area right here from the y equals a square root of x all the way to the x-axis. And then I'll find out this area right here, which looks a whole lot like a triangle. I might even just use geometry to figure out that area. And then I will add that together. Okay, I will not do subtraction. All right, so I guess another question is, what is that intersection there so that I know where to go up until? So I don't know. You could set them equal to each other and do some algebra 2-ish kind of stuff where you square both sides and blah, blah, blah. But me personally, I mean, I would probably just say, well, does it work if x is 1? Does it work if x is 2? Does it work if x is 3? I would do it.
If you take any time drawing it, it's really obvious as well.
If your sense of proportion is good, and you're like Mark, when you draw, it's very obvious that you're in good shape with that. But so where is it, Mark? Can you tell where it is?
It's at 1, 1.
It's at 1, 1, right? When x is 1, the square root of 1 is 1, and when x is 1, 2 minus 1 is 1. So 1, 1 works for both. So we're going to integrate from 0 to 1 of root x dx, but then we're going to add to it a half times base times height, because that's going to be the area of this triangle right here. This intersection here is at 2. So my base is 1 and my height is 1. And then I would, continue from there. I don't think I need to finish this off. I think Mark probably has at least one more thing he'd like to say that I might not have addressed yet. But this would be, we've done this several days in a row, these kinds of antiderivatives, fundamental theorem, blah, and then here, that's just going to be a half, and then I'm going to add it together, get my final result.
Yeah. Yeah, I could grab your screen and show the final result, but I already got it, so
okay.
That's fine.
But earlier you said there was an example
there was
you wanted to see.
There was something that you did. You had an example that it didn't come up. So I think if you go back to your very first one.
Mm-hmm. Oh, okay.
Just throw it up there as a reminder.
Number 4, this one?
Yeah.
Okay.
Oh, and nope, it was the second one. It was the.
No.
Yeah, this one. Okay. Because it didn't come up, but it comes up in fundamental theorem, and Verge was really good at showing it every time. But if that 2x minus x squared was your bottom function, and you were subtracting it in the integrand, make sure that you wrap it in grouping symbols.
Oh, if you're subtracting a binomial,
yeah, if it had not been x squared plus 5 or something like that, where it was higher up, just make sure when you subtract an expression as your g of x that you did those grouping symbols around it, so that subtraction comes off the entire antiderivative.
In fact, I think we might want to look like that for a warm up tomorrow to make sure.
That's not a bad idea.
Yeah, so we'll look for something like that, where if you don't use grouping symbols on that second function, if that second function has more than one term and you don't distribute that negative, basically, you get in the hot water pretty fast.
Yes.
And that's algebra, that's not calculus. But it messes up your calculus. All right, so we'll see everybody tomorrow. Mark's probably going to go back to the
I'm trying, yeah.
PowerPoint, but we'll see everybody tomorrow for our last day of the week, where we're going to wrap up some of these ideas from Unit 8, and we plan on doing quite a few free response questions, in addition to maybe one multiple choice, just that are very topical for this unit. That's our plan anyway.
And I just want to say, because I'm sure it's happening to some students as well, because we're getting emails from teachers. Again, you can use your smartphone to point at this QR code. You can't click this bit.ly, but you can, that bit.ly is underneath. If you expand the descriptions, either with a right arrow or down arrow, depending on whether you're on the app or on a computer, that is in the description of every video, and that'll take you to the Dropbox where all of our resources going all the way back to March 25th are. And again, here's just our information about our wonderful information about our exam. And I'm gonna try and catch some fish because we're done, right?
We're done. We're done.
Thanks, everyone.
Mark's virtual screen game is it's pretty awesome.
And if you guys aren't here tomorrow because it's a holiday, catch up on Monday with 2 videos. We'll see you when you come back.
That's right. Bye, everybody.
Bye.